Okay, here's the first physics video of the term, and I don't know why we've called it a temperature check test. Yeah, this is the beginning of the Year 12 course, so it's for the new 12 AS level students. It's basically an intro to physics where we taught them about uncertainties and units and practical skills. So we've done this just to see if how they're coping early on in the course. We only made it 23 marks, so they had plenty of time, and 40 minutes was available to them. Okay, so let's just go through my answers. I went through it with my students today, and the first one is a multiple choice question. So the student is measuring the diameter of a steel wire in order to determine the cross-sectional area. So if you know the diameter, you know that the equation for the cross-sectional area would be pi d squared over 4, and it says that the percentage uncertainty in the measurement of diameter was given as 1.8%. So we know the percentage uncertainty of d, so the percentage uncertainty of A is 2 lots of d because it's squared, so you just double the percentage of the uncertainty of d, so it's basically 3.6%. So the only one that gives 3.6% is B. Okay, so that's the first question done. So you need to know that whenever you multiply multiply terms, the uncertainty is the percentage uncertainty will be added, and since they're both the same percentage uncertainty due to d squared, yeah, then they'll both be 1.8%. Question 2 is more to do with kinematics, or the Suvat equations. So there's a proposal to build a train tunnel underneath the Atlantic Ocean, yeah, from England to America. And the suggestion is that in the future, the trip of 5,000 kilometers could take as little as 1 hour. Okay, so let's assume it's taking 1 hour. And it says you can assume half the time is spent accelerating uniformly, and the other half is spent decelerating uniformly. So basically, the speed's going to increase uniformly from u to a maximum velocity, and then it has to decelerate back to 0 for the end of the trip. Okay, so half the distance is during acceleration, so that'd be 2,500 kilometers. You've got to change it into meters. We know that half the trip will be 30 minutes. You've got to change it into seconds. We know the initial velocity was u, and all we've got to do is work out a. So we want s, t, u, and a. So that will be s equals ut plus half at squared, because they want us to show that the acceleration can be simplified to this, is about 2 meters per second squared to one significant figure. So that's one significant figure. So roughly 2. So for the acceleration phase, we're going to use half the distance. So A is going to be 2 times S, which is 2.5 million meters, times 30 minutes. You've got to change that to seconds, square that, and you'll get an answer accurately-ish. Or I've done 4 significant figures. Never put all the figures on your calculator down. It looks messy for the examiner. And that to one significant figure rounds up to 2 meters per second. So we have proven, we have shown that. Shown that means prove it mathematically. The next part says calculate now the maximum velocity, the peak of that graph that I sketched. Well, since we know u, a, and t, all we got to do is use v equals u plus at, very much like a GCSE question. Yeah? So I've used my accurate value, and I get 2,778 meters per second. Again, to 4 significant figures, I round it up to 2 significant figures, because the data provided is accurate, really, maximum to 2 significant figures. Yeah? If you have a look in the question, they've given 5,000 kilometers and 30 minutes. So really, 2 significant figures is all they need. Then it wants you to calculate the resultant force. So it's like GCSE, F equals ma, Newton's second law, yeah, to decelerate the train. So obviously the force required will be the same as the accelerating force. Initially, they've given you the mass of the train in standard form. So all you've got to do is put the numbers in, very much like a GCSE question. And 2 significant figures, again, is all you can really quote to. This would be the answer to 3 significant figures, and then you round it up, and that's the 6 marks, 2 marks for each section. Okay, here's the mark scheme if you want to stop the video and have a look at it in your own time. Part A, B, and C. Okay, so I'll let you just stop the video when you want to, and then we can go into question 3, which was another question 1 here, but it's question 3 in this practice paper for our students. A student carried out an experiment to determine acceleration of free fall. Using the apparatus shown, there's a release mechanism which starts the timer, and then there's a timing plate at the bottom. When the ball hits it, it will stop the timer, okay? And usually these timers can be accurate to a millisecond. So it says that the uncertainty in measurement of t was plus or minus 3%, and the uncertainty in measuring the height was 1%, and they did it for different values of height. Because in this method, which is core practical 1, for those of you doing edXL linear or modular, this is the first core practical that you have to do, and you have to do it graphically. You can't just put one value into the equation and work it out. So they said the student plotted a graph of t squared against h, and they've done that deliberately to make the algebra more difficult for you. And from that, they want to determine the value for g. Yes? So if you put t squared on the y-axis and height on the x-axis, then you're basically doing, you're investigating s equals ut plus half at squared, but ut is 0. So s equals half at squared, where a is g, and you can change the subject of the equation to make it t squared, because t squared is on the y-axis, yeah? So you've got t squared on the y-axis, and you've got s on the x-axis, okay? So basically, if you've got t squared on the y-axis and s on the, which is h, yeah, the height, on the x-axis, then the gradient of this graph, and you've got to draw the line of best fit like I have, going through as many points as possible. If you draw the line of best fit, you can then work out the gradient of this graph. Always use the largest triangle possible and show your values on the graph like I have. There's the change in y, or the change in t squared. There's the change in x, or the change in height, which in algebra, in the Suvat equations, would be s, yeah? So you can show how much it goes up, yeah, over how much it goes across, and from that work out the gradient, okay? So if you understand how to do the gradient, then in the next section, you've got to show how you get the value of g. The student concluded that her value for g, which must be from the gradient, was consistent with the accepted value for g, which would be 9.81. Okay? Comment on the student's conclusion, but your answer first should include a calculation of g from the student's data. Yeah? So in other words, from the gradient. So from the gradient to the graph, which I showed you just now, you can show that the gradient is delta y over delta x, which in effect is delta t squared over s, which will give you this value. So the gradient calculation is just maths, and again, I've shown it to 4 significant figures. Okay? Now, since we know it's a straight line, y must equal mx plus c. So whatever is on the y-axis, in this case, t squared, goes on the left-hand side. Whatever is on the x-axis is there, and therefore, because y equals mx plus c, whatever is in front of the variable that you put on the x-axis will be equal to the gradient. So 2 over g must equal the gradient. Yes, it's predicting that there's no intercept, and that's because the ball dropped from 0 velocity, so ut in the equation for s equals ut plus half at squared is 0. Yeah, so if remember, here ut is 0. So if ut is 0, it should go through the origin, but you see they haven't got the origin included in this graph because they don't need it to calculate g, and they've spread their data out to make a better graph. So you don't always have to go to the origin. All right, so once you know that the gradient, what you calculated, you know that the gradient must be equal to 2 over g. So if you change the subject around, you can see that g must be equal to 2 over m. Do the division. I've quoted to 3 significant figures. It's 8.48 meters per second. Well, the correct value should be 9.81, so you're not that close. But there was a total uncertainty of the data which they gave us in the first question. If you remember, the data was given here as being 3% for time uncertainty and 1% for height. Okay? But the equation is t squared and s. So you have to double the percentage uncertainty for t. So that's 6%. And then you add the percentage uncertainty h because it only comes in once. So 7% total uncertainty. So that will give you gravity of 8.48 from the student's data, plus or minus 7%. So if you add the 7% to the maximum value, 7% of 8.48 is 0.6. So now you're just going to 2 significant figures because of the uncertainty. That's all you can quote. So it's a maximum gravity you can get from this data of 9.1. So the student's conclusion, I've put, the student's conclusion is incorrect. The data or the graph or the line of best fit, and my line of best fit is good, I've drawn it well, gives a maximum value of 9.1 meters per second squared, which is still below the accepted value for g, which is 9.8, to 2 significant figures. The student's range would be from 7.9 to 9.1. So where the student concluded that her conclusion is consistent with the accepted value, it's not. Yes, it's below the accepted value, as you can see. And you can also work out the percentage difference of her value, to the true value. So that's another way of doing it. And she reckons she's only got 7, but I think she's probably going to be more like 12% out. Okay, and here's the mark scheme. Okay, that's how you get the marks. Calculation of gradient, 1 mark. Use of s equals ut plus half at squared, 1 mark. Total uncertainty, 7%, 1 mark. Calculation of percentage difference or range, I use the range of her values of g. And then a judgment of her conclusion for the final 5th mark. Okay, and you can see even they got 8.67, I got 8.48. Okay, and that depends on how you drew the line of best fit. Okay, so you can stop the video and have a look at the mark scheme. Finally, this is a slightly more theoretical question. This actually comes from a year 13 paper. Yeah, so it's a proper A-level question, and it's about a filament lamp. So the filament lamp, let's do it in yellow this time. The filament bulb is the voltage to current characteristics, which is one of the early chapters in the edXL course. They've drawn a curved non-ohmic variation of potential difference to current, and they want you to determine the resistance, at 7.0 volts, which is here. So you draw the line up with a ruler, line across, it comes to 1.44. Divide one by the other and you get 4.86. I've done to 3 significant figures, but the data is only given to 2 significant figures. So you need to round it up to 4.9, and don't forget the unit. If you miss the unit, you won't get the 2 marks. Okay? And then they say sketch a graph of resistance against potential difference. This time resistance against potential difference. Well, we know that the resistance at 7 volts is 4.9, so that's 1 point you know. And they want you to sketch it from 0 to 7 volts. Well, if it's 4.9 at 7 volts, below 7 volts, it will be less hot, so the resistance will be below 7 volts, okay? So you know R will get lower than 4.9 ohms, so that's 1 mark. So you know it's going to be lower at the intercept, and because R increases with voltage for a bulb as it heats up the lattice structure, okay? So 3 marks, you look on the mark scheme, see how they're given it. So you need to go to the intercept, and it's not going into the origin because the resistance of the wire isn't 0, even if there's no voltage in it. It still has a resistance. It's not a superconductor, okay? So that's a good point to clarify. And finally, the last bit of this paper is 6 marks for explaining the variation of resistance with potential difference for a filament bulb, yeah, in terms of its particle behavior, yes. So they want you to talk about the lattice structure vibrating. They want you to explain how the voltage increases the vibrations, yeah. So key words could be the collisions, yes, rate of collisions with the lattice structure between the conduction electrons and the lattice structure, or free electrons, yeah. So they keep colliding, they're going to increase the resistance, and they'll find it more difficult to get through when the lattice structure is vibrating more vigorously, which happens at higher voltages. So you've got to be able to explain all this in a clear way. You need the correct amount of depth, detail, and clarity, as I always explain to my students, to get the 6 marks. You see, this was a final question from one of the papers, because you can see it's the end of a section A of a paper that I got it from, okay? I'm not going to say which paper right now. Okay, so there's the mark scheme. Hopefully you can see it. And here are the indicators that they're looking for. As the voltage increases, the acceleration or the velocity or the electron speed increases. Yes? So the energy of electrons increases with voltage because obviously they're being accelerated towards the positive end. And these faster electrons can transfer energy in collisions with the lattice structure or the ions of which make up the filament. This increases the vibrations and therefore the temperature of the ions or the filament itself. And as it gets hotter, the amplitude of vibrations increases, yeah? And of course, if the ions are vibrating more vigorously, they're also going to impede the electrons which are trying to be accelerated to the positive side of the power supply, and they will collide more often because the lattice structure is getting in their way. And I think I demonstrated that in class to my students, how that would work if an electron's trying to go through and the students are the lattice structure. If the students keep moving in and out of their chairs, it will stop someone walking between the rows of seats in a classroom. And that is a good way of having an analogy. And then due to the increase in resistance, the current then doesn't increase in line with or in proportion with the increase of potential difference. Yeah. So if it's a clarity that you can get 4 marks from just mentioning these things, and then they add 2 depending on the clarity of your answer. And here it says for 2 marks, answer shows a coherent and logical structure with linkages and fully sustained lines of reasoning. In other words, you don't confuse the person reading it throughout the answer. So anything that's contradictory could lose you a mark. Okay? And that's basically the quick run through of this first assessment for our Year 12 students. and I hope you found it useful. And if you're one of my students, I'll be doing more of these to put on the YouTube channel for you to be able to follow and then go through it again outside of the class, because there's not always enough time with a large group to go through your individual questions. Hope you found that useful. Don't forget to make sure that you subscribe so you know when future videos are uploaded, you'll be notified. Okay, thanks for watching. Bye for now.